Okay, the goal of this video is to talk about circular apertures instead of slits, basically. Holes, circular holes instead of slits, and see what happens here. All right, and so what happens here, and I'll show you an example in a minute. This is an idealized picture here. Laser light's gonna come in, hit a circular hole right here in the screen, and then the pattern you get, instead of being fringes like rectangles, we're going to get circles. This central bright region is called the airy disk. All right, and then so we see a bright central disk, and then kind of a dark ring instead of a dark fringe, and then a bright ring, and then a dark ring, and then a bright ring. And just like before with the single slit, we saw the intensity pattern was huge in the middle, and then it basically dropped by a factor of 20 or so to get to this one. And so what happens here, when I try to show you this, remember the central region is going to be about 20 times brighter than this one, and then they get weaker from there on out. So you'll see some pattern that looks like this would be a profile. If you just cut a line through it like that, right, there'd be a big peak in the middle. But yeah. So without further ado, let's try and look at this pattern here, and let me see here. I think if I go like this, so there's the entire classroom, and what I've done here on this screen right down low, you could see two dots. I've got two lasers going through the same hole, and I'm going to see if you can actually see the lasers there. Give me just a second. So here's what's going on. I'll come over here, and I'll have to walk up to the front, so give me just a second. I've got two laser beams right here and here, shining, and they're both aimed at a tiny little hole right here. So they're both hitting the same hole. So you can see it's two dots here, one right there. And then we're going to go through and we're going to see those patterns over here on the screen. Let me go up to the front so I can see as I'm adjusting the monitor. So those two spots are showing up right here on the screen, and I'm going to zoom in on these. Whoops. So you can hopefully see this pattern a little bit. Keep going. All right, and so it's pretty faint there. I'll turn off most of the lights in case you can see a little better. I'm going to double check the focus. All right, and so that's the best I can do to show you this pattern. And we see, I'm coming over to point at some stuff. The airy disk is this central bright circle. And then I can see it pretty clearly. Again, this is one that's going to look a lot better in a real classroom. You can see the rings around it. And so alternating bright and dark rings. And the pattern gets a little bit messy. There's a thing called laser speckle in there too. So let's go back up to the board and talk about this before we get to a worked example. Let me do this. Hold on. Go back to the board, and I probably should turn the lights on so you can see. That would be nice. Just a second. Okay. So again, I used two laser beams, so we're kind of looking down here at this lower page now. So I had two laser beams that were shining in, and they were both angled so they hit the hole, right? And there's some angle here, theta. Here's the circular aperture, and we saw these two different rings. So what does it mean for us to resolve these two sources? Meaning to distinguish them or be able to tell it's not a single light source. So for that to happen, we get this situation right here, where I would say it like this. The two airy disks slightly overlap, and it's such that when one central maximum is centered at the other's minima. So when you have for example, if I named these so I could discuss them better, let's say this is source 2 and this is source 1. The maximum of 1 is centered on the first minimum of 2. And likewise, the maximum of 2 is centered on the first minimum of 1. So, right, you want this bright spot to be located at the other one's first minimum, if that helps you understand that. And there's a bunch of math you could do, but we get sine theta minimum. This is the minimum angle to resolve, is 1.22 lambda over d. And now let's get real here. These angles are almost always tiny, very, very tiny. So usually in a lot of books, you'll just see it written like this. 1.22 lambda over d equals theta min. Think on the units. Meters, meters. This is in radians. All right. And this has a name, the Rayleigh criteria. So that's usually what people have decided to agree upon as two sources are just barely resolvable, right? This kind of looks like a big blob over here. And so you're saying, yeah, it's a big blob, but I can just barely kind of tell the difference between this being two blobs versus one big blob. Any smaller angle than this, it basically looks like one big blob that you can't distinguish at all. All right, so how does this end up working out in a problem? Let's take a look. There's one little trick here. So this is 36.14. I'm on page 55. Those plots that I was looking at were on page 54. Sorry about that. So we have a car, two headlights. So they're spaced by some distance. And I think in my solution, I called this distance W. Assume the two sources are point sources. So the two headlights, we could think of one as source 2 and one as source 1. They're both point sources. Headlights produce white light, so there's some red, there's some green, there's some yellow, there's some magenta. But 555 is green, it's kind of in the middle of the spectrum. So let's just assume these produce, excuse me, at 555 nanometers. And we're wanting to resolve them. So let's draw this picture here. And these problems confused me a lot when I was first learning them, so maybe I'll mention something here. This angle is theta, right? That's the minimum angle to resolve them. Now keep in mind, here's an eyeball over here, and we're assuming that the pupil diameter is 3.00 millimeters. I think, I just want to confirm that. Yeah. So now in this case, clearly this is not drawn to scale. This 3 millimeter eyeball or pupil looks as big as this 1.3 meter spacing. So in practice, right, if we could really draw it, the pupil would basically be like a tiny dot here, right? Smaller than that. And so, okay, great. So now that's one thing. Another thing, I'm going to show you the trig based off the half angle. So this little angle right there is theta over 2. And I'm going to show you the trig on the half angle, and then afterwards you'll be like, oh, can't I just make this a right triangle? Yes, you can, and I'll show you all that. So let's take a look at this. What is our goal in this problem? So our goal is this. How far away is the car when you can just barely resolve the headlights? So when you see this just barely resolve, you get this on your paper. Theta minimum equals 1.22 lambda over d. All right, so we know lambda and we know d. That's looking good, so we should be able to get theta minimum But how do we relate theta minimum to this distance? What we're trying to find in this problem is the distance away. So I'm just going to call that L. And so I will point out that this distance right here is not W, but W over 2. And so I'm going to take, I'll say, tangent of theta over 2. And I guess this is theta minimum because we're trying to find the minimum here. So theta 2 minimum is equal to, let's see, W over 2 all over L. All right, and so in this case, but wait a minute, isn't this a small angle? For small angles, sine theta equals tangent theta equals theta in what units? Radians. I should double check. You can see the screen. You can't? Okay. So we can just rewrite this as equals theta minimum over 2. All right. After this, I think you could go ahead and solve this out. So from here, and the solution's written up. It's got the numbers in there. But maybe let's do one more step here. We see that, what are we looking for? L. So the 2's drop. And then, let's see, what am I looking for? I'm looking for L. So L is W over theta minimum, which is this. The D flips to the top, making sure I didn't screw up. Theta minimum is 1.22 lambda over D. The D gets flipped to the top. So you can punch in numbers for that. And let me just see what I got in case you're wanting to not look it up. Which problem was this one? I got 6.09 kilometers. So you can double check that. See if you get that. Maybe I'll do it right now just in case. All right, W. What was W? That was the width. 1.375 times the diameter, well, that's the pupil, that's 3, E negative 3, then divide by 1.22 and divide by lambda, 555, E negative 9. I got that same result. Okay, now what happens here, I guess maybe I'll show you one other picture here that a lot of times you'll see. I'm just going to draw this picture a slightly different way. I'm going to angle it slightly. It's not looking too good here. Give me a second. So there's theta minimum. Here's source 1. Here's source 2. If the angle is small enough, you can kind of think of this distance here as L, right? And this is W. And so notice that's what I was kind of talking about here. The divide by 2 ends up canceling out. So in a lot of books, you probably will see somebody just says tangent theta equals W over L, even though this doesn't look like a right triangle. It doesn't look like a right triangle because the scale is absurdly exaggerated, right? So if you actually drew this to scale, right, if this is 1.4 meters, the length that is involved is 6 kilometers, so 6,000 meters. So that, when you do that, this looks basically like 2 lines right here. And it looks almost exactly like a right triangle. The difference between this kind of triangle and that kind of triangle, it's essentially a right triangle. And that's why these look goofy. Read the solution if you want to see more on that. I think that's enough on that.